processor, and then we were coming up with this next generation NVIDIA next generation Grey-Hopper compatible with this kind of strategy. So when we talk about scalability, right, our architecture is actually very scalable, all the way from machine learning to general purpose processor. And you can see here, our first generation Grayscale has this T cell right in there. It's actually a 10-6 element we call. And then the whole system is actually composed together, right, with this 10-6 core with the 2D torus connected now. But inside this 10-6 core, starting 2016, we already utilized the RISC-V as an embedded processor in there. So there are 5 embedded processors in there. Each one is responsible for their specific task. Right? So as you can see the picture here, one processor is designed for receiving the packet right, from the other computation unit, deposit to our local memory, and then the other one is actually responsible for sending the packet, by fetching the packet, sending it to the other processor. And in the middle 3, there's 3 processors responsible for transfer data from the local memory right, and to the computation unit. And then the central CPU is responsible for issue the instruction right, to the computation unit. So this is an example how we're actually using the RISC-V processor in the embedded environment right, to achieving the AI computation acceleration. So this 10-6 element is actually the basic building block for our system. Right? It's become a licensable IP for us as well. So if any people are actually interested in this, right, it's actually a composable element. You can form in like a 50 teraopt operation, or you can even form in a large system like we are building for. So this scalability actually doesn't stop at the chip level. Right? Like I mentioned, the second generation one-hole processor we're building, we started adding the Ethernet capability in there. That actually allow you to scale to the much larger system. Right? So the Ethernet system, like this is a demonstration system we're actually building today. Right? So it composed 32 of the N300 system with the board shown there, but you can see that the black socket there is actually Ethernet port. Right? So this is actually natively connected to each other. Right? So the board is actually natively connected to each other to the Ethernet port without external switches. Right? And forming this 4U server, right? And achieving 12 petaflop DFA at 6 kilowatts. So this is a large system used for training and high performance inference. So the scalability coming from the architecture itself with the 10-6 unit with the RISC-V processor in there, and then connect to the NOC, and at high level you actually connect to the Ethernet port and forming a much larger system like this. Right? So we can actually natively connect to each other, right? To 30,000 of this chip together without external switch. So this is very different from what the NVIDIA is proposing. So they have going to embedding switches, but this is natively connected. So there are a lot of talking about is RISC-V ready for high performance computing. Right? So Tensor actually heavily invest, from my perspective, is already ready, because if you heavily invest on the software stack, like us, we do in the past 6 years, right? This is a complete demonstration, the software ecosystem we have for machine learning. So you can see that we have a machine learning framework being translated using the TBN to our internal operation, right? And then we actually parallelize it, and then based on the computation demand, and then we generate the computation graph, right? And based on the graph dependency, we compile and place and route and put it on the 10-6. Right, so we load down to the RISC-V binary, and then load down to the 5 processor you actually see there, and perform the machine learning task. So the whole flow is actually designed as a fully automated task, right, for all the machine learning, popular machine learning framework to optimize implementation. So you actually create a very high quality result without no manual effort, because most of the machine learning architect, right, data scientists, they're not interested in understanding what's the machine, right, what's the hardware is about. Right? We also plan to do is that this solution has to be scalable as well. The same compiler should be targeted on one chip, right, even one 10-6 core, right, to all the many thousand chips. Right? So this is our goal. So from my perspective, this is a very good example that you can use in the RISC-V capability and then focus on with the right focus on the investment, right, and building a complete solution for high-performance computing like the AI we are doing today. So changing gears a little bit, so this is our machine learning, right, AI chips. But changing gears that we're going to talk about the RISC-V high-performance CPU processor. So you can think about the computation is actually falling into two spectrum, right? AI computation is a very specific mental multiplication, right? And then general compute is going to the other domain. But from our observation, right, the future AI is actually going to be a combination of both. Like for example, the GPT-3 has a lot of table lookup, right, the TB cache. So for that kind of cache lookup, it's very fragmented, right? So machine learning is actually, the theory is actually good on the computation, which is batchable, right, and can be issued together. But there are a lot of computation in the current existing machine learning framework actually require the CPU to do it because the access is fragmented, the address is fragmented, right? So the general purpose, high-performance general purpose compute is actually very important for that as well. So that's why we introduced, designed this high-performance RISC-V processor. We think this is disruptive because it's an AOI decode machine. We believe that you will be achieving projected Zen 5 performance in 2024. So this one will be in the function-wise, we are RBA 23 profile compliance. It has an advanced branch predictor. It's an AOI decode machine. It's a 3 low store units, 6 ALU in the branch, 2 branch units. And you have 2 256 vector units, 2 floating point units. So this is really a high-performance design for the data center. And then the design is well under the way. You can see this is a PD die we demonstrated, and then we already able to boot in the Linux. So in the lab with the emulation. So we scheduled to take off on Q1 next year. So I just talked about what the scalability for our AI product. So CPU as a companion processor for the AI processor, we actually need the same kind of strategy to address the co-processor, companion processor concept. So when we design this AOI decode machine, we actually make sure that it can be architecturally parameterizable to supporting 6Y decode machine, 4Y decode machine, 3Y decode machine, and 2Y decode machine to ensure that we can address the market, right, with the different PPA requirements. So this is easier than said than done, right? Because your RTL environment need to be parameterizable. Your verification environment needs to be parameterizable. So this is a very cool strategy we have. So in a very short 2 years, we actually come with an IP portfolio of a high-performance superscale RISC-V processor, right? While the other company trying to achieve in 10 years. So you may ask, like, why do you need a CPU in AI? Like I mentioned, right? So there are a lot of tasks, like for example, virtualization, security, system management, and computation kernel setup. Those kind of management tasks you have to done by the CPU. Right? So we integrate the RISC-V CPU in our black hole. That means it can do all this management tasks by replacing the x86. Right? So that's when the RISC-V processor can do the general compute for maintaining the security while the AI is doing its work, doing its best work on the acceleration. Well, the other part we actually foresee is actually the AI computation in the future, like I mentioned, right, will be highly heterogeneous. In 1 minute. So it will be highly heterogeneous, and that means that there will be a lot of computation needed to cooperate between the CPU and then also the GPU. Right? So in this way, we actually build a processor enable them to actually have the interconnection topology and also the computation capability that they can talk to each other very easily. So we actually spend a fair amount of time to investigate that transformer overlay technology and also make sure that CPU has same technological capability like the other acceleration element in there. The processor can be also using for the network computation acceleration. I don't want to go through this. Right? So we designed a CPU, we also can integrate the DPU acceleration in there, so CPU can do that for that purpose. And then in the last couple of examples, I actually just demonstrate to you, right? So how the RISC-V is being applied in our AI processing and also for the general purpose processing and also for the future chiplet technology. So the scalability is not only coming from the computation of itself, right, but also coming from our chiplet strategy in the package level. So, like we're using the our ASCOM process building this really high-end, the easiest chiplet, which contains 128 core, right, with the CC Newmark, full CC Newmark project in there. So it has it's a local I/O coherent connect and the memory connection and the hierarchy connected to the coherent traffic. So it's actually a very high-performance CPU platform. And then we're building as a chiplet I showed there. And then this one can be composed with our AI accelerator as a heterogeneous computation platform. And of course, the chiplet can be using also as building a high-end server, like in this, so you have DDR memory and then have a chiplet in there. So I just demonstrated that Tensor has a scalable technology all the way from AI acceleration, like computation element. Right? You can use it to compose a chip, right? And then we can use in chip level, we can have the Ethernet port to scale out. And also our CPU process family is also scalable. So with all this technology, right, we can actually address the market from the edge device to edge server and to even the HPC in the cloud. Right? So this scalable technology actually able to address a wide range of the product we are making today. So that's why this milliwatt to megawatt actually makes sense for us because our architecture is designed that way. So our recent cooperation with the Samsung, with the recent cooperation with the LG, actually demonstrate the powerfulness of our technology. So, like I want to mention again, right, this scalability, we're using RISC-V technology to build this scalable CPU family, and then we're building a scalable AI computation element. We're using the chiplet to make the scalability even higher on the package level. Right? So we think Tensor using the RISC-V technology, and then also machine learning technology is a unique position in this